All right, I think we are good to start. We are at the top of the hour, so we can go from here. Uh, let's before we dive into the presentation itself, I'm going to do a quick overview on the community stats and updates and what's happening with Hoodie in general, and then we'll proceed to our expected talk today with Amazon Engineering, and then we'll open up some time for the Q&A. All right, so that's pretty much the agenda. So in terms of the community updates, we have great momentums going on in the project. We have Hoodie 1.0 that is being planned for, very soon. So that is super interesting to have that. But in terms of like the last month, whatever has happened, I just pulled up a 1 month's data. We have 55 merge pull requests. There are 32 issues that are closed. 18 new issues being worked on. So 55 requests merged by 24 people. So thanks to all the contributors who take the time and contribute to the open source project to make Hoodie successful and bring in all these amazing features. And like I said, we have like around like 4,565 Slack users. Slack is a great place to be there, to ask community questions, learn about how Hoodie is being implemented in the community today, and also like talk one-on-one with PMC members, I guess. In terms of the like vanity metrics, some of the numbers like GitHub stars, good momentum there, and 24 contributors, we talked about it, who landed PRs in the last month. And if you are not following us on social, which you should, because we post a lot of stuff, what's happening in the the overall space with Hoodie, with lake houses. So I think it's a good place to be there and like get all the recent updates that's happening. Also, like I said, the Slack channel, I just left the QR code over here. If you're interested to join and being a part of the community, do some of the interesting contributions. Maybe like start with Hoodie Rust, which is like a brand new project as well. So maybe that's a good way to start from there. With that, I'm going to pull up our speakers, Jason, Setu, and Abhishek to the stage. Hey guys, you guys are all on stage now, and thank you so much for joining us today for this session.
Thank you.
What I see from the community is like they're super interested to learn about what you are doing, how Hoodie is being implemented with Nexus, and all the learnings that you have basically gathered from this overall experience. So thank you so much for the time, and the stage is for you guys to like take it forward. So Jason, feel free to like share your screen, and I'm going to add it to the stage.
Yes. Okay.
All right. I think you're good.
Cool. You guys are audible? You guys can hear me?
Yes.
Okay,
Perfect.
cool. All right, cool. So for this talk, we'll talk about powering Amazon unit economics with configuration Hoodie. You saw the title from the meeting, from the LinkedIn event invite. Yeah, so basically we built something called Nexus that help us to use configuration to help us power Amazon unit economics. What is unit economics? We'll probably learn in the next slide. And the presenter today are me, Abhishek, and Setu. Okay. Introduction. So let me start off by doing some introduction for what's our business, what are our specific use cases. So we're part of Worldwide Amazon Stores. Under Worldwide Amazon Stores, we're a business called Selling Partner Services. The major mission for selling partner services is to enable long-term success for our sellers by providing very top quality, trusted shopping and selling experiences for our sellers. And then we also provide a very set of powerful analytics for our sellers so they can grow their business, and in turn our business. Our specific org under selling partners services is profit intelligence, where we basically own a product called contribution profit, which is mainly the stuff we'll talk about today. So what is contribution profit? Contribution profit is a metric we produce by aggregating, allocating, and compute data from a lot of different Amazon store teams sources. We take sources from, say, ordering. We take sources from fees, transportation, and then in the end we produce a lot of unit level economic metrics. One of them being contribution profit, which the term is Googleable. It's a pretty standard business metric. It basically tells us for a given single Amazon unit what is the profit. Yeah. And once we produce the data, we will vend the data to other downstream decision-making teams, such as pricing, where they'll use our data to automatically determine the price. We'll give it to forecasting so they can know what would be the probability of this specific ASIN in the future. And we also give our data to finance team so they can work with our vendors to determine what are some of the stuff that they should sell or we should sell, when to self-selling, etc. Yeah, so we kind of do it for the entire worldwide web Amazon store. So one of our unique challenges is we really need to support a huge amount of different retail and FBA businesses. And we also do digital, I believe. Yeah, so there are a lot of different use cases, and the profitability behaves very differently. So for example, try before you buy. It's a business in Amazon retail where customers will buy like some clothes, and then they would try a clothes, and then they would later on determine if they should buy it or just return it. So that's one of the business use case, and the other business use case can be like Kindle ebook, where it's very straightforward. So yeah, one of our unique challenges is we need to support a lot of different retail businesses. Yeah. So the outline of this talk is we'll first go over our history with data lakes. This concept of contribution profit exists in Amazon for I think 15 years. We started doing data lake 10 years ago. It's been a long time. We've had many iterations with data lakes. So just go through some of that and how we landed on Nexus. The second point would be we'll talk about Nexus, which is a config-driven framework for running, orchestrating Spark jobs, potentially more jobs than Spark, and managing our data lake. And then we'll go through some of our learnings with Hudi. There are three subpoints with our learnings. The first one is throughout the process, we learned what type of table structure we want for our specific use case and what type of concurrency control strategy we want. The second one is we learned how to better manage metadata table through Hudi configurations, what to do, what not to do. We'll talk about it once we get to the slides. And then costs. What are we seeing is the cost with Hudi, and what are some of the savings strategy that we found potentially with using Hudi. And then we'll just go through some numbers, some preview. As part of the Nexus work, we have deprecated 300,000 lines of SQL so far. We'll deprecate more in the coming years. Yeah. And now I'll give it to Sethu to talk about our history with data lakes.
Thank you, Jason. Before we go into what is Hudi, how we are using Hudi in Nexus, I wanted to give a brief context on how CP, basically contribution profit, in short we call it the CP team, how CP has used data lake over the past 10 plus years. As Jason said, in our team, we calculate the unit level economics of things that Amazon sells, which means we've been dealing with big data processing for 15 plus years. But initially, we were just processing data and publishing it to a data warehouse for reporting purposes. But over the past 10 years, we've realized benefits of owning our own data and maintaining our data lake, which gives us a lot more control. And over a period of time, we've gone through multiple versions of data lakes that we have used. We started off with our own custom data lake on S3 with our own custom query language. Then we moved to unstructured Redshift ETLs, which are built on top of the previously mentioned S3 data. We then moved to AWS structured / semi-structured Redshift EMR ETL jobs. And more recently, in the past 5 years, we've started ingesting not just batch sources, but also streaming sources. And we've used Flink to process some of the streaming ingested data, but still used the homemade Redshift ETL compaction to be the data lake solution. And finally, Abhishek is going to talk about where we are today in Nexus and how we are using Hudi as a data lake solution rather than our own custom solutions that we have mostly been playing around in the past 10 years. Before I go further into any of these specific solutions that we've used, one thing that I wanted to highlight here is that all of these solutions we changed because of differing requirements that we get from business. Initially, we started off with something very simple, like, hey, we produce data once a day, we give it to our customers, they consume it, and we're done. But over time, to improve the accuracy of the data that we produce, given the amount of business decisions it's powering, we've had to restate the data that we've given customers continuously. In fact, today, we actually restate hundreds of days of data that we've computed every day, on top of the data that we need to produce for that day. Jason, can you go to the next slide?
Mm-hmm.
So this is in the previous different iterations I talked about. This is one of those iterations, which is the structured Redshift load job. The reason I picked it up is I wanted to highlight in here one of the problems that we had with all of our excuse me, one of the problems we've had with all of our data lake solutions, which is our business logic is existing in our processing layer, and our business logic exists in our data lake querying / processing layer, which means we've coupled our business logic with our engineering solutions completely in all of our previous iterations. What this means is that it becomes very hard for somebody who's not on our team to come and understand how we are computing the unit level economics that CP is computing. And with Amazon's growth and business, us being the gatekeepers for all of Amazon Retail's business logic is a scaling problem for Amazon as a whole. Besides that, as you can see here, there are multiple layers of Redshift jobs that are working on top of the unstructured Parquet data that are produced by our processing layer. And this is our differentiation between processing and data lake. But in fact, data lake also does a bunch of processing in Redshift. So there is no clear separation of responsibilities the way we've structured the system. Next one, Jason. Thank you. So this is our more recent solution where we started addressing some of the problems that I mentioned before. In this solution, at the processing layer, we are unifying the business logic and providing our customers with a way of controlling the business logic at the processing layer. And we've started ingesting at this iteration streaming inputs for our system, and we've used Flink batch mode of Flink to process those stream ingested sources and combine them along with our existing batch sources and produce unit level economics so that our customers can use them. The problems exist in the sense that once the processing is complete, our data lake is still in-house custom, and it uses Redshift ETLs, which once again has a lot of business logic embedded within them. Our own data lake started dealing with scalability and maintainability issues with the scale of Amazon, and any changes that we made to any business logic required extensive testing, not just at the processing layer, also at the Redshift layer, which further complicated our ability to move fast and make changes for new businesses that Amazon was launching. Towards all of this, then we came up with a solution, which was Nexus, which is what Abhishek is going to be talking about, where not just is the goals of or the problems that we've stated so far, we are trying to address all of those. We are trying to separate the concerns of processing and our data lake solutions, while at the same time giving our customers the ability to manage business logic or business configuration that they want to use so that unit level economics can be computed away from the execution layer, which is Spark, Flink, Hudi, or whatnot. With that, I'll hand over to Abhishek to talk more about Nexus.
Thanks, Setu. Yeah, I'll start off with what is Nexus. Nexus is our current solution to the problem that Setu just walked us through. Nexus is a config-driven data processing platform that allows customers to express their business logic as simple declarative configurations. The users or business owners are expected to only interact with this configuration layer. Nexus platform goes from this user-provided business logic to producing the final outputs by internally generating the relevant workflows that in turn execute the jobs, the tasks, and in turn produce the output tables or datasets. At a high level, there are 4 main modules to Nexus framework. There's the configuration layer, there's Nexus Flow, Nexus ETL, and Nexus Data Lake. As Setu was mentioning, we're trying to isolate the layer at which the customers interact with and they're able to onboard their business logic. That's the configuration layer. The rest of the modules I'll briefly walk through. Next slide. All right. Nexus Flow, again, part of the Nexus framework, handles all the orchestration responsibilities. It operates at what we call the Nexus workflow abstraction, which is basically workflow modeled as config again. Users are able to define the workflow as config if needed, but in most of our cases, we generate the workflows from the configuration layer. At a high level, Nexus Flow operates at 2 layers, the logical layer and the physical layer. At each layer, we enrich the user figure and user input with more information until we have an executable workflow. Logical layer is where most of the inference magic happens. This is where we go through the tasks that needs to be executed, what are the dependencies, what are the inputs to the task, outputs to the task, building the tag of tasks, and attaching some runtime figure information. Physical layer is where the actual execution of the workflows happen. For all intents and purposes, it is a lightweight abstraction over step functions, DynamoDB, and view lambda. One of the core theme of Nexus, among the other benefits we just spoke about, is it is very extensible, which goes for Nexus Flow as well. It uses a federated model, so whenever we need to onboard new tasks, we are expected to only add new configurations. There's no the amount of code that needs to be added to support new tasks are very minimal. Some of the current task types that are there are Nexus ETL jobs, which I'll go through. Some legacy ETL, Redshift queries, and wait for dataset is something we use to handle the data dependencies between jobs. Next slide. I'll briefly walk over some sample Nexus Flow configuration. There is no need to understand the exact syntax here. Just the main takeaways here I would like to show is we use Amazon Ion data format to describe most of our configuration, actually all of our configuration. The workflow : and the task binding : that you see describes the type of the config element. So here, workflow : indicates that it's a workflow and Nexus Flow understands that. And we're looking at 3 jobs that it needs to execute. I also wanted to include one sample of something we call a meta config, which is config describing how we pass other config that Nexus Flow understands. I won't go too much into detail of the task binding itself, but here we are saying for a task that is of type job, look at inbound. For understanding the input dependencies for job, we look at something called source. To understand the output dependencies for a job, we look at something called sync. Next slide. Next, we look at Nexus ETL. Nexus ETL takes the responsibility of the actual ETL or the compute or data processing within the Nexus framework. We can treat Nexus ETL as the main library to go from a Nexus job abstraction to an executable Spark job that can run on EMR or any data processing platforms. Nexus job is basically, again, a job abstraction, which is defining job as configuration. A job here is modeled as a list of operators that needs to be executed. The operators are usually have a bunch of sources and sinks and transforms in between. Today's transforms, they include both built-in Spark transforms like join unions. And it also includes a lot of custom transforms that we use heavily, which are usually tied to Spark UDFs. Nexus ETL currently supports only Spark jobs, but the concept of Nexus and job as configuration should apply to other processing frameworks. We have a light version of it for Flink as well. Next, we'll go over the sample for Nexus ETL. Here, again, there's no need to understand the exact syntax, but we're looking at the job type. It has 4 operators. It's taking 2 sources, joining them, and writing to a sink. So the source type describes the sources along with some of its information. The multi-join is a custom UDF we have, which allows users to join multiple sources. And sync basically says the final output. Just to show an example of related config, a relationship is something that is used by multi-join to further describe how to do the join. For instance, it describes what are the join keys for different tables. Click. More related configuration to the source. We have file connector and table. This is not necessarily Nexus ETL config. This we internally describe as Nexus data lake config. Here, for a given source, where file connector describes the physical aspects of the table, things like if it's a glue table, what is the physical name of the glue table? And table describes the logical aspects of a table, which is things like the schema, the attributes that it has, and the partition keys. Sometimes it also has the distribution keys as well. Next, we'll go over Nexus data lake. So this is the final module for Nexus. It is a storage layer, which today is mostly Hudi tables. This is where user config drives catalog management, which includes automated table creation, schema inference, schema evolution. Sometimes there are, like I said, hints given to the processing layer, things like the distribution keys. All of these Nexus data lake configurations tie back to either Nexus ETL operators and also use sometimes by Nexus Flow to do dependency management. One example is if we are looking at the very first job that's executing within a workflow, it looks at Nexus data lake configurations like the file connectors and tables to understand what external dependencies it needs to wait on before executing that job. All of our Hudi and data lake interactions go through Nexus ETL and Nexus Flow today, but there are plans in the future to introduce direct higher order APIs to support other query use cases. Next, I'll go over Nexus data lake sample config. On the left-hand side, the data lake config kind of represents a parent config, which acts as defaults for all the tables. So we have different stages, different catalogs to use. Some of it is also Hudi configuration. If you look at it, there's pre-combined field write operation. And right-hand side is a sample file connector for a particular table. Most of it is filled from the defaults, and some of it is specific to this table. There is, we built a bunch of, so if you look at partial update, it's something that's built into Hudi right now. We initially started off with a custom solution, but later once Hudi had that feature, we started using the partial update feature. So that's one tiny detail of how Hudi details are included in the data lake configuration. Next, I'll hand over to Jason to cover some of our data lake learnings.
Cool. So over the past 10, 15 minutes ish, we talked about a lot of abstractions, how we build to basically serve our user better, which are usually finance and business people. We need to build a lot of abstractions to bridge the gap between what they understand and what actually gets executed in the physical layer. So a lot of the learnings we have will talk about what's happening in the physical layer. So one of the learnings we obtained was the concurrency control. So when we started off building our data lake and then satisfy our business requirement with Hudi, we thought of the old design, which is on the left, where we will have different Nexus jobs that read sources and then writes to a monolithic Hudi table. So to deal with this multiple writer scenario, we started with optimistic concurrency control, which is kind of the default option that the Hudi offers. Yeah, the reason we thought this would be a good idea is for schema management. We want to make it easier for customers to move one field from a given output of a job to another job. So if we have a monolithic Hudi table, then it will just work. We have a partial update. The Avril payload that the Hudi offers in their interface. Yeah, so that would just work. But however, when we run this stuff on the left in shadow, we realize because of our update pattern that Sethu mentioned, there's a ton of update going to the same table, and some of them will go right to the same partition. And Hudi has a check on write to see if there are other writers writing to it at the same time. So because of that, we started seeing failures in our jobs, and then we realized we have to change our table structure. Because everything is defined in config, we were able to change it pretty fast. So the new table structure that we settled on is on the right, where we have jobs that read sources, one or multiple sources, and it will write to a single Hudi table. So that drastically reduced the amount of concurrent write to a Hudi table. From on the left, I think we get 60 concurrent writes, 60 writes to a single partition a given day to two, basically on the right. And then later on, we will run a join job that kind of joins these Hudi table via either a snapshot query or incremental query, and then we publish to a combined Hudi table. So yeah, after we we pivoted to the new table structure, we were able to minimize the concurrent insertion by a lot, and this is the table structure and design that we're running in production right now. Another learning we got was how to manage metadata table, which is enabled by this config Hudi metadata enable equals true. So when we first developed with Hudi, we started with synchronous cleaning, but due to some internal reasons, there was a lot of S3 connection being opened and closed, not as part of Hudi, but through our other processes. I think they're mostly for authentications. Yeah, so because of these S3 connection that's being open and closed, it made S3 connection really slow. So we thought maybe if we turn off the synchronous cleaning, that would allow the job run faster, which allow us to serve our SLA better. So we switched to asynchronous cleaning, which we did observe it worked. It actually cleaned the data. It actually cleaned the physical data in different partitions. But what we discovered later on is that the metadata table through these config that was enabled was not getting cleaned by the async cleaner. We found the GitHub issue. We worked with One House people who the community, and we realized that the asynchronous cleaner doesn't really clean the metadata table, at least in the version that we're using. I think it gets fixed in later version, which is 1.x, 1.0. Yeah, so we realized the metadata table were not being cleaned, and the metadata table itself is very important in to making sure the performance of our job runs well. So we switched it back to synchronous cleaning, and everything worked. It's interesting tidbit. And then the last learning that we want to highlight is the cost related to Hudi. Most of our table, like currently 100% of our tables are copy on write. We are working on developing our merge on read, but the costs are, we'll mostly talk about copy on write tables that we have. We also have different type of workloads, as Sethu mentioned. We have daily workloads where 99% of traffic falls into one partition. These are basically what the orders got, what are some of the shipments that got shipped to customers today, for example. And then we also have update workloads, which evenly spreads across 30 to 90 partitions. These are workloads like what was refunded, like customer sent a refund. These will be part of update. And when we observe the cost, we realize basically 70% of the cost falls into put request alone, and then put and get requests combined for about 80 to 85% of the cost. One of the cleaning strategy we have is also not very aggressive. So we do, due to auditing purposes, we will store data indefinitely. So far, we'll probably look into some solution how we want to handle the storage cost better. But what we are observing now is most of the cost goes into requests, because it's constantly reading the existing data and then putting no new data, because we're doing copy and write. And because of our workloads, for daily workloads, it would touch a lot of partitions. So because of this, we looked at some of the saving strategy. The first one is S3 intelligence steering. This has a lot less to do with requests, because at first we thought it is mostly storage, but it turns out to be mostly requests. Yeah, we did pilot it on some of the tables we have. Basically, as in AWS, if you're using S3, it offers something called intelligence steering, where they automatically switch the storage classification of your data to, I think it's from normal, like standard, to infrequent access to like deep glacier or something. So we piloted on our table. We do see some cost reduction. It very much depends on when you get the data, and depends on your update pattern as well. So yeah, it's something to try. And then we also have we also looked into EMR auto scaling as a potential cost reduction strategy. We ran a hackathon, and yeah, the EMR offers something called the scaling, and you can scale your cluster up and down based on specific metric. We have to turn off some Spark parameter, but yeah, the end result, it saves, I think, 50% of the cost comparing to what we had previously. So these are the saving strategy we tried. Obviously, there's cleaning. Cleaning would save, depending on your cleaning strategy, it would save a lot of money for you. And yeah, we'll now go to some numbers. So as I mentioned before, as part of developing Nexus, we deprecated 300K lines of SQLs. There's a lot of jobs that we turn off, and then we replace them with Hudi. And currently we maintain about 1,200 tables, and increasing because we're developing more and more use cases, usually using Nexus data lake, and they will be built on top of Hudi. All of them gets updated 5 to 15 times a day. The total data size we currently maintain is about 3 petabytes, and I think we launched into production this year, so it will be increasing, and with 1 petabytes of data getting added and getting cleaned every month. But it is ever increasing. Every day we updated hundreds of billions rows across our Hudi tables every day. So one thing I do want to highlight is in the previous slide, when we had our homegrown version of Data Lake, which is built by 1 or 2 developers. It took a couple months, and then we've observed there's certain scalability issue with it, mostly because to really have a good working version of Data Lake, it takes a long time. Hudi really helped us with that. It saved a ton of developer days. so we can better focus our energy on scaling our business use cases. Okay, that's pretty much all the talk. I want to say special thanks to Sridhar, Diego, who helped reviewing the slides, and then Alex, Xiaowei, Janavi, Chushan, Jaya for building Nexus. And thanks to Deepankar, who helped us organizing these talks, and special thanks to Shian, who really helped us a lot. Well, we worked with him a lot through our journey with Hudi. Yes, that's all. Thank
Awesome.
you guys.
Thank you so much, Zishan and the team. Yeah, it's really great to see and hear like the scale that you guys have implemented Nexus at, and the future, of course. Like that's super. Like we want to be future proof in terms of data architecture, right? I think that's what we kind of like move towards too. I think that's what is super interesting to see as well. So we do have a couple of questions that we might want to like take it now. And again, for our audiences, like, it's a synchronous thing. You can just post your question on LinkedIn. We will also have a video later on YouTube on this recording. So feel free to like watch the recording there. And if you have any questions on that, again, we are there to like look around and, get your questions answered from the team. All right. So I'm going to like pull up some of the questions that we have from the audience. One question from Baldomir is, I think it's related to maybe Nexus in specifically, maybe what data source or sinks are supported. Is it possible to define a custom data source or sink? If anyone, if anyone.
So it is definitely possible to define custom data sources and sinks. We already have defined internal data sources and sinks, which is not directly on AWS, but internal to Amazon. So Nexus Flow and basically the overall Nexus framework does provide interfaces to onboard new data sources. Most of it is just configuration.
And just to add, I think through our development with Nexus, something we learned is it's sometimes easier to make things harder for people to build.
Right.
To build things. It might be unintuitive, but we
we
potentially want to limit the set of features we offer so people don't add weird things that might break existing patterns. But
makes sense. Okay, and that control is basically like is it like some kind of a governance layer or some kind of like internal like that you guys control over as a team, or is it specifically like sitting around in a different layer that you kind of like initially talked about in your presentation?
Specifically it is the usually it's the configuration that kind of adds this guardrail of making sure everything is standard and not no one is doing one-off patterns.
Right. Sounds good. The other, it's okay. I think you maybe have answered a little bit of that, and maybe you've tried this thing. But have you tried? I think DynamoDB logs. I think you discussed a little bit about it in your optimistic concurrency control thing. It says, is DynamoDB base logging best effort or guaranteed? I'll let you like add your like context to it, that, and I can also like fill in some details.
Yeah. Okay. Sure. We did. I can ping some of the GitHub issue we filed. But we did look at DynamoDB concurrency. We are using it. Without using it, I think, it definitely helps to a certain degree, because we did run jobs without using Dynamo, and it does not support any concurrent writes. I think the Hudi checks would just fail. So it definitely helps. We are using it, but it doesn't fully lock the table, which I believe, because we're using because I think the only file OCC offers with it, the only concurrency control strategy offers is optimistic, so far. So it would fail when there are multiple writers writing to the same partition.
Exactly. And you've also given the high contention like with your like scale of tables, right? You have so many like tables, so OCC typically works with the assumption that contentions are like the conflicts are rare itself, and basically leads to a lot of failure. That's kind of like how the principle of OCC works. So I think that's an interesting angle to look at, given the scale with what you're implementing, because in general, if you had like a few tables, it would have been like absolutely fine in general. But I think just to add to that as well, Ravjot adds that, we had a similar issue. We also moved from monolith table to isolated tables, and we implemented our Redis-based lock, which helped them in their concurrency control thing. So yeah, I think there are different like databases, and maybe that particular locking factor, it depends on that particular external thing as well. So I think that is something to add as a context. But yeah, thanks for filling us in. One question again from Kirti Manu is like any metrics around average target table size and record count, incoming load record count, and the percentage. And feel free to like
our tables are ever growing. I would say the record count itself is a bit sensitive. I don't know if I can talk about that.
Yeah.
But I can talk about the percentage. I think we're doing synchronous cleaning. So I know the amount of data we insert and delete roughly is the same, but it's ever increasing. For daily data, I would say 90 to 95% are actually insert, and and for daily workloads, 90 to 95 are actually inserts, and the rest are updates. And then for update workflow, it's all updates. Where we're restating data.
To just add to that, I think it depends on the different tables. Of the 1,200 tables, I think we have some of them which are predominantly inserts, and some of them which are predominantly updates. It depends on the pattern itself. A very quick example would be returns would have a lot of updates, because we are as and when returns happens, you'll have to update it. Whereas things which don't get which we don't have to retroactively do, they will be just
That makes sense. Thank you so much for that additional context there. There was another question on like, it's more about like an experimental thing, maybe like, have you experimented merge on read tables for your use case? If it's a more like low latency based writing and stuff.
We have thought about it. In the beginning, we kind of avoided it mainly because we were planning for our table in the end to be just directly queryable by customers. We don't really want, we really want good query latency, because our tables are external. People need to read it very efficiently to help make the business decisions. Recently we've been thinking there may be some tables that we maintain can be merged on read. We will probably explore that next year.
I see. Sounds good. I think it's from a personal like perspective as well, like from my side, is that I wanted to ask is for organizations who are looking at like this kind of data lake implementation at a scale. I would not say like maybe at Amazon scale, but at least pretty much like similar scale, given the the velocity of data now being generated. What are some of the essential like kind of decisions or like the steps that you had to like that kind of Hudi helped in that process, like to take you in that journey when you're thinking about like a future-proof implementation of a data architecture? And it can go like in different angles. Like it's not like linear to me. Yeah.
Okay, I have two angles, I guess. One of the main thing which I kind of talk about in the numbers is really it saved a lot of development effort, and because it's open source is getting better. We saw the Hudi table got better. From like version 11 to version 14, I think we saw some performance improvement. Also, I think Hudi 14 also introduced like a record level index. Is it 14? Yeah. So it's it like on the development effort front, I feel like it's a no-brainer to use something open source like Hudi, because it just really save a lot of our time. So we can focus our energy on like building for our businesses.
Makes sense.
Yeah, I don't know if other people want to add more.
I think that's the main value. The development effort goes significantly down, and you're working on something reliable and reviewed by so many people.
Awesome.
Yeah. Another point I can add is stability. We have so many tables updates. If there's any stability issue because we're updating so many tables, our operation would be very bad.
Yes.
But Hudi for us is very stable. We update so many tables. We don't really care about them. We just assume they go through. right now, operationally, if something goes wrong, usually almost never is because of Hudi. It's usually because something else. Yeah.
Got it. So stability, reliability, scalability. I would just add scalability towards that as well. But yeah, I see the high, kind of message coming out. So that's really good to know. And kind of a follow up as well. Like, how did you even decide to go with Hudi in the first place? Like, was it something that you've heard of, or was it something that came naturally in general, like from your architecture perspective?
Initially, Hudi was suggested by one of our senior data engineer who left the org since as a potential solution. Because that was around the time when we're building our homegrown data lakes.
Right.
I looked at a couple options: Hudi, Iceberg, Delta Lake. Delta Lake is we cannot use that. It's not very AWS-y. So there was Iceberg and Hudi, and when we decided, Iceberg didn't really have. We also had Flink back then. Well, we still use Flink.
Yes.
Hudi is more geared towards streaming data, writes, updates, incremental query, things like that. Then Iceberg. So we
got it.
Yeah, we went with Hudi.
Makes sense. Probably one last question that I had from the audience is from Rabjot. Like, are there any additional query engines integrated to read the Hudi tables, or is it just whatever you discussed?
We use AWS Athena.
Okay.
I think you guys probably work with Athena for a bit as well, because Athena has pretty good integration with Hudi. Yeah. Right. It queries really fast, surprisingly fast. Awesome. Even with we can do query pattern select star from Hudi _Hudi commit time larger than a certain time, and it's a gigantic table. It takes 3 seconds to give us a result.
Awesome. That's good. That's good to hear. All right, I think that is all. I just wanted to take my time, and thank you guys for taking your kind of work time off and helping the community understand what's being implemented at your scale. I think this is a really good way for being an engineer in the past, for me to see and take some inspirations from here, because the use cases are not new. They have been predominantly there from over the years, and like you said, you guys have been building the strategy for so long within Amazon. So that's really good to hear and see. And thank you so much from the Hudi open source team here for joining us. And we hope this is beneficial to the community. And thank you so much once again.
Thank you so much.
Thank you.
All right.